Good evening, ma'am. Good
Good evening, sir.
Yes. Make me the host, ma'am. Good evening. And Lakshmi, good evening. And
Good evening, sir.
so we'll start with the theory part before we do the MCQs. All right. So we have learned with the 15 group elements in the last class. We have completed with phosphorus also. MCQs we will learn possibly later. Exams are coming, so I'll finish off with the theory part of it. Now the next is called as the 16th group element periodic table. In 16th group element, we have 1 3-mark question, and I will go a little faster so that we can finish our syllabus possibly, which is required for the exam. 16th group elements. The 16th group elements are called as chalcogens because this chalcogens means ore forming. Ore forming. So ores are in the form of metal oxides, metal sulfides. So therefore, the 16th group elements are called as chalcogens because of the property they can form, they can exist along with ores. Now in the 16th group element, the elements present is oxygen, sulfur, selenium, tellurium, polonium. See, oxygen and sulfur are typical non-metals. Selenium and tellurium are metal character and non-metal character. Polonium is a metal. And you should remember, it is a reactive metal, and it has half-life period very small, a very short half-life period. All right, polonium is a radioactive metal. They can ask you for 1 mark. In this chapters, generally a 1 mark question is asked from noble gases. That is 18th group element. In 18th group element, and that also is question number 8. Question number 8, part A. Question number 8 will be from 18th group element, and it should be a 1 mark question. So anyways, now polonium is a metal which is radioactive, and it has a very short half-life period. Now properties. Now oxidation states. So these elements show various oxidation state from -2 to +6. It shows -2 oxidation state, +2 oxidation state, +2 oxidation state, +4 and +6 oxidation state. Can you hear me?
Yes, sir.
Yeah. So -2, +2, +4, and +6 oxidation states. We will take some examples of elements showing -2, +2, +4, and +6 oxidation states in the later stages. Oxygen do not show +6 oxidation state. So oxygen do not show +6 oxidation state. Other elements show +6 oxidation state due to the absence of d orbitals. So oxygen will not show +6 oxidation state because it does not contain d orbitals. If it contains d orbitals, it also will show +6 oxidation state. And polonium also does not show +6 oxidation state due to inert pair effect. So polonium also does not show +6 oxidation state due to inert pair effect. So sulfur, selenium, tellurium, all this will show +6 oxidation state. The stability of -2 oxidation state decreases due to increase in atomic size. So when you go down the group, stability of -2 oxidation state, increase in atomic size. and decrease in electronegativity. Oxygen shows -2 oxidation state in general. Now, for an example, if we take water, in water as a whole, the charge is 0. Oxygen, I don't know what is the charge. I take it as X. Hydrogen, we know it's a first group element, +1. +1 into 2 is 2. So X will be equal to -2. Generally, oxygen shows -2 oxidation state. But if you take an example, OF2 or O2F2, in OF2 as a whole, the charge is 0. -1 is the charge of fluorine. Fluorine is the most electronegative element in the periodic table. Since fluorine is the most electronegative element in the periodic table, fluorine will have -1 charge. When it has -1 charge, -1 into 2 is -2. Oxygen, we're trying to find, we take it as X, so X becomes +2. Oxygen can show +2 oxidation state only with OF2. Likewise, if you take this molecule as a whole, the charge is 0. Fluorine is -1 into 2, -2. Oxygen, we have to find X. Since we have 2 oxygen, we'll take it as 2X. So 2X will be equal to 2, X will be equal to +1. So oxygen can show +1 oxidation state also in O2F2, remember. The stability of +6 oxidation state decreases and +4 oxidation state increases due to inert pair effect. So as you go down the group, the stability of +6 oxidation state also decreases, but oxidation state of +4 increases due to inert pair effect. Now, so far what we have learned is, you should remember oxygen family, 16th group element is also called as chalcogens because it can form ore. And the first elements present in the 16th group is oxygen, sulfur, selenium, tellurium, and polonium. Oxygen and sulfur are nonmetals. Selenium and tellurium are metalloids, and polonium is a radioactive metal. Oxidation states are -2 to +6. Oxygen does not show +6 oxidation state because of the absence of d orbital. Polonium also does not show +6 oxidation state due to inert pair effect. And oxygen shows -2 in general, but it also can show +2 and +1 only with fluorine compounds. Now, this is with the introduction to the 16th group. Now, the properties, physical properties are general. As you go down the 16th group, atomic size increases. There's no explanation required. You've been learning it from the first POC, right? Because as we go down the group, atomic number increases, new shells are added, new periods are formed, therefore atomic radii increases, and also ionic radii. The next property is electronegativity. Electronegativity is the ability to accept electron. So if you observe this, as we go down the group, non-metals to metals, metals are electropositive. Metals are electropositive. That means electronegative nature decreases down the group. Electronegative nature decreases down the group. So when electronegative nature decreases down the group, that means metallic character increases. Metallic character or electropositive character increases. Now, the next property is elemental state. Oxygen exists as O2, diatomic, due to the presence of p-pi multiple bonds. Sulfur exists as S8. Selenium exists as Se8. Tellurium exists as Se8 due to the absence of p-pi multiple bonds. So sulfur, selenium, and tellurium exist as octaatomic elements. Oxygen exists as diatomic element because O2 contains only 2 atoms. S8 contains 8 sulfur atoms, octa element. You should remember why oxygen exists as O2 because of the presence of p-pi multiple bonds. Selenium, sulfur, and tellurium exist as S8, Se8, and Te8. The next property is ionization enthalpy. Ionization enthalpy, ionization potential, ionization energy all means the same. It is the energy required to remove the outermost electrons from the isolated gaseous atom. See, in the 15th group, for an example, if you take nitrogen, atomic number is 7, 1s2, 2s2, 2p3. In the p subshell, we have 3 orbitals. 3 electrons are filled here, like it is half filled. But in case of oxygen, atomic number is 8. The electronic configuration is 1s2, 2s2, and 2p4. When we take 1s2, 2s2, 2p4, 1, 2, 3, and 4. This is partially filled. Partially filled. So half filled is more stable than partially filled. That means ionization energy of nitrogen is much greater than oxygen because nitrogen is much stable. Or we can say 15th group elements are having more ionization energy compared to the 16th group element because all the 15th group elements will have half-filled electronic configuration. This is with one point. The second point is ionization enthalpy decreases down the group. As we go down the group, what happens? Atomic size increases. Since atomic size increases, the electron affinity, the electron attraction force of the outermost electron with the nucleus will be less. Therefore, ionization energy also will decrease. Are you following? I'm going a little faster. I hope that
Yes,
you're
sir.
Next is electron gain enthalpy. What is electron gain enthalpy? This electron gain enthalpy is also called as electron affinity. Energy released when an electron is added to the outermost shell of an isolated gaseous atom is called as electron gain enthalpy. Oxygen has less negative electron gain enthalpy than sulfur because of the small size. See, less negative electron gain enthalpy. Negative gain enthalpy means it is exothermic. When an electron is added to the outermost orbit, energy is released. The release in energy is represented by a negative sign. So that's why we call it as negative electron gain enthalpy. Oxygen has lesser negative electron gain enthalpy because oxygen is smaller compared to sulfur. From sulfur to polonium, electron gain enthalpy becomes less negative due to polonium because of the increase in atomic size. As the atomic size increases, electron gain enthalpy becomes less negative. Next, melting point and boiling point. Melting and boiling point increases with atomic number. As the mass number increases, melting and boiling point increases. Oxygen has much lower melting point and boiling point than sulfur because oxygen is diatomic, sulfur is octatomic. So that means the mass of SH will be very high compared to O2. Therefore, the melting point and boiling point of oxygen will be lesser compared to that of sulfur. Now coming to the shapes. Now, hydrides. Hydrides are generally represented as H2E. E stands for elements of 16th group. When we say elements of 16th group, if it is O, H2O. If it is H, H2S. If it is Se, H2Se. Like that. Now, all these are called as hydrides. Hydrides of 16th group element. Water is also an example for hydrides of 16th group element. Now, in case of water, we've learned the structure of water. It has a bent shape. Water has two lone pairs of electron. And also we have learned VSEPR theory. Because of VSEPR theory, what happens is lone pair repulsion will be greater than lone pair bond pair repulsion, greater than bond pair repulsion. We have learned it in chemical bonding chapter. Therefore, even though the hybridization of oxygen is sp3, the expected shape is tetrahedral, the shape changes to bent because of the theory called as VSEPR theory. We can understand and justify. Now here, the boiling point or the bond, this is boiling point of water, 373 Kelvin, hydrogen sulfide 213, H2Se it is 232, and H2TE is 269. As the mass increases, boiling point increases. See, hydrogen sulfide is a lesser mass compared to H2SE. Boiling point increases. But in case of water, even though the mass is less, the boiling point is in water, intermolecular hydrogen bonding is possible because oxygen is highly electronegative. Therefore, intermolecular hydrogen bonding is possible. Therefore, water has higher boiling point compared to all the other hydrides. Water is a liquid while other hydrides are gases. Why water is a liquid? Other hydrides are gases because water forms intermolecular hydrogen bonding. There is force of attraction. That is why water exists as a liquid, and all the other hydrides like H2S, H2SE, H2TE, they all exist as gases. Acidic nature. Water is less acidic compared to hydrogen sulfide, compared to H2SE, and compared to H2TE. This is because He bond length increases down the group. Therefore, bond dissociation enthalpy decreases down the group. So acidity is the ability of the molecule to release H plus ion. So these all are bigger atoms. As the size of this atom increases, to break the bond and give H plus ion becomes easier. Therefore, acidity increases. Acidic nature increases. Thermal stability. Thermal stability, when we say stability due to heat, is called as thermal stability. Water is more stable compared to all the other hydrides because in case of water, we have intermolecular hydrogen bonding. Due to the intermolecular hydrogen bonding, water is thermally stable compared to all the other hydrides. Reducing character, less reducing compared to H2PO, hydrides of polonium. And boiling point, we have learned hydrogen sulfide is lesser than H2SE. H2SE is lesser than H2TE, which is lesser than water. I'm not explaining that again because we have learned it here in detail, the boiling point concept. Reactivity with oxygen. E is the element of the 16th group. Reactivity with oxygen. Reducing character of dioxides decreases down the group because oxygen has strong positive field which attracts the hydroxyl group, and removal of H plus becomes easy. It's highly theoretical, which is not there for your second PUC. Don't worry about it. EO2 and EO3 compounds. 16 group elements can form oxides like EO2 and EO3. For an example, I can say sulfur dioxide, sulfur trioxide. Likewise, selenium dioxide, selenium trioxide, goes on like that. All right. So oxygen can react with other elements of 16 group to form like that. Now, likewise, halides can react with 16 group element to form EX2, EX4, and EX6. Now, for an example, maybe we can take we can take SCl2 is not possible, but SCl4, SC6. We can take other halogens, any other halogen. The stability of halides decreases of the order F minus is greater than this, which is greater than Br minus, which is greater than I minus, because as the size increases, the stability decreases, the bond dissociation energy decreases. Fluorides are more stable because of steric hindrance. Because fluorine is very small, therefore it will not be hindered by other elements. Therefore, it is more stable. Sulfur hexafluoride, sulfur tetrafluoride, like this. Questions will come back later. MCQs will learn later. Now we'll have to learn with dioxygen preparation, ozone preparation, all that. A few of the important questions we'll have to learn. 2 markers question we have to learn, and 1 3-marker question we will be learning later. Now, it is dioxygen. The heading is dioxygen. What is this dioxygen? Oxygen is represented as O2. Since we have 2 oxygen atoms, it is named as dioxygen. Now, how can we prepare dioxygen? Dioxygen can be prepared in many ways. One of the method of preparing dioxygen is by thermal decomposition of potassium chlorate. Potassium chlorate is represented as KClO3. This is potassium chlorate. This potassium chlorate, when we heat it in the presence of manganese dioxide, this potassium chlorate will decompose to give potassium chloride, giving you oxygen. They'll ask you how dioxygen is prepared in the laboratory. You should tell dioxygen is prepared in the laboratory. Potassium chlorate and manganese dioxide in the ratio 4:1 in a hard glass test tube. When potassium chlorate, KClO3, potassium chlorate. When potassium chlorate and manganese dioxide are heated in a hard glass test tube in the ratio 4:1, potassium chlorate decomposes to give potassium chloride, liberating oxygen gas. One method. Second method is this hydrogen peroxide on catalytic decomposition, finely divided metals. Hydrogen peroxide, when heated with finely divided metals, this hydrogen peroxide also decomposes to give water and giving you oxygen gas. Please try to write the physical states every time. So oxygen is a gas. If you don't write the physical state, you can lose a part of the marks in the exam. So you should. The third method of preparing, this is the lab method. Third method of preparing, these all are thermal decomposition, all because of heating, right? Thermal decomposition of oxides of silver and mercury. Silver oxide, when we heat, if you remember in Ellingham's diagram, we have learned the graph for silver oxide and mercuric oxide is above 0 line. Delta G becomes positive. When delta G becomes positive, they are thermally unstable. Just by heating, they decompose to form metal silver, giving you oxygen gas. And if you take mercuric oxide, it decomposes to give mercury and give you oxygen gas. So these are the methods in which we can prepare oxygen. And also we have by lead oxides, lead tetroxide, lead dioxide on heating gives lead oxide, monoxide, and giving you oxygen gas. This is not recommended in the syllabus. No, not in syllabus. Okay. Now, one of the method, large scale, how oxygen is prepared. You remember this, in large scale, large quantity, dioxygen, what happened? Dioxygen is prepared by electrolysis of water. When we electrolyze water, we get large amount of oxygen. We can prepare large amount of oxygen. So acidified water or dilute water, when we electrolyze, oxygen gas is liberated at anode and hydrogen gas is liberated at cathode. So large quantity, we can prepare oxygen on electrolysis of dilute acid or water. Properties of oxygen. Physical properties of oxygen. Oxygen is a colorless gas. It is a odorless gas. It doesn't taste. And it contains two unpaired electrons. If you remember molecular orbital diagram, molecular orbital theory, what we have learned in chemical bonding, and I've taught you molecular orbital diagrams. When you write the molecular orbital diagrams, you will understand that oxygen has two unpaired electrons. in the anti-bonding molecular orbital. Therefore, it is paramagnetic. Dioxygen directly reacts with all metals, gold, platinum, and silver, and some of the non-metals and some noble gases. They directly react because oxygen is more reactive. It directly reacts with metals. Now, with metals like calcium, sodium, magnesium, aluminium, it forms their respective oxides. See, calcium is a metal which reacts with oxygen to form calcium oxide. Likewise, if you take sodium, and this sodium reacts with oxygen to form sodium oxide. Both are basic in nature. They are basic in nature. Calcium oxide in water gives calcium hydroxide. Sodium oxide in water gives sodium hydroxide. Therefore, they are basic in nature. Now, if we take aluminum when you heat it with oxygen, it's all happening at high temperature. Aluminum, when you heat it with oxygen, we get aluminum oxide. It is amphoteric oxide. It's amphoteric oxide, meaning it can behave like an acidic oxide or it can behave like a base. Therefore, it is amphoteric oxide. Phosphorus, when you heat it with oxygen, you get phosphorus pentoxide. P2O5 exists as a dimer, P4O10, and phosphorus pentoxide is an acidic oxide. It is phosphorus pentoxide. Now, carbon, when you burn carbon with oxygen, you get carbon dioxide. Carbon dioxide is acidic in nature. We know what is roasting and what is combustion. Roasting is sulfide ore. Burning sulfide ore in the presence of oxygen is roasting, and combustion is burning a hydrocarbon with oxygen is called as combustion. So directly, oxygen can react to form basic oxides, amphoteric oxide, as well as acidic oxides. This is with respect to metals and non-metals. See, all these are metals. Sodium is a metal. Phosphorus and carbon is a non-metal. And these all are compounds. Oxygen reacts with zinc sulfide. Oxygen reacts with methane. These all are compounds. Now, questions we'll learn with respect to oxygen also later. I hope you followed with this oxygen concept preparation. Are you there? Now, next is oxides. Oxides. The compounds of oxygen and other elements are called as oxides. Compounds of oxygen and other elements are called as oxides. Now, types of oxides. The first one is acidic oxides. Oxides which forms acid when combined with water will be called as acidic oxides. So any oxide, when dissolved in water, when it forms an acidic solution, then it will be called as acidic oxides. Generally, non-metallic oxides are usually acidic. So sulfur dioxide is a non-metallic oxide. Cl2O7 is a non-metallic oxide. CO2 is a non-metallic oxide. N2O5 is a non-metallic oxide. So sulfur dioxide, when dissolved in water, you get H2SO4, H2SO3, sulfurous acid. Now, this is an acid. This is neutral. So that means the nature of SO2 should be acidic. So oxides, when dissolved in water, if it forms an acidic solution, then it is called as acidic oxides. Generally, they are non-metallic oxides. Now, metallic oxides are mostly basic in nature. Basic oxide dissolve in water, forming base. Dissolves in water to form sodium hydroxide. Calcium oxide dissolves in water to form calcium hydroxide. Potassium oxide dissolves in water to form potassium. All these oxides, when dissolved in water, it gives bases. Therefore, these all are called as basic oxides. We've learned acidic oxide, basic oxides. Next is amphoteric oxide. This now Al2O3 is an amphoteric oxide. We know that HCl is a very well-known acid. So when it's allowed to react with HCl, we get AlCl3 and 3H2. This clearly shows Al2O3 is behaving like basic in nature. And we know that sodium hydroxide is a very well-known base. When sodium hydroxide is allowed to react with alumina, Al2O3, we get a complex, sodium aluminate. And here clearly we understand that Al2O3 is behaving like an acid. So therefore, side, which is amphoteric in nature, can behave like a base. Now, neutral oxides, these are oxides which are neither acidic nor basic, like carbon monoxide, nitric oxide, nitrous oxide. These all are neutral in nature. They do not react with, they don't behave like an acid, or they don't behave like a base. Therefore, they're called as neutral oxide. We have mixed oxides. The one more type of oxide is mixed oxides. Oxides made up of two simple oxides. Oxides made up of two simple oxides are called as mixed oxides. Now, for an example, Pb3O4. It is made of PbO2 and 2PbO. Likewise, we have Fe3O4. It has Fe2O3, and also we have FeO. So oxides which are made up of two simple oxides are called as mixed oxides. Questions we will learn. I'm rushing through the topic. The next topic what we have is ozone. Here they can ask you a 2-mark question. Preparation of ozone, they can ask you for a 2-marker. We'll try to learn that. Preparation. Ozone is O3. Importance of ozone also we have to learn. We will learn that importance of ozone a little later. Now, preparation of ozone. How ozone is prepared? Ozone is prepared in the atmosphere at an altitude of 20 to 25 kilometers from the Earth's surface by the reaction of oxygen or UV radiation gives ozone. So this is the reaction. Oxygen, which is present about 25 kilometers above the Earth's surface, in the presence of absorbs UV radiation to form ozone. This is in nature. Now, the laboratory preparation. How do you prepare ozone in the laboratory? Ozone is prepared in the laboratory by passing silent electric discharge through a pure and dry oxygen. 10 to 15% of oxygen is converted to ozone. So it is prepared by passing silent electric discharge through ozonizer, which contains pure and dry oxygen. Only 10 to 15% of oxygen is converted into ozone. If we take a long tube, ozonizer, into this we'll have an anode and we'll have a cathode. And into this we take low pressure oxygen gas and we pass silent electric charge. The potential is very, very, very low. When we take silent electric discharge, what happens? Oxidized to ozone. Only 10 to 15% of that will be converted to ozone. Since only 10 to 15% of oxygen is converted to ozone, the ozonizer will contain ozone and oxygen. Therefore, it is called as ozonized oxygen. It's called as ozonized oxygen. Did you follow this? They can ask you the preparation of ozone in the laboratory. How ozone is prepared in the laboratory? Prepared in the laboratory by passing silent electric discharge, low potential electric discharge through an instrument called as ozonizer. Only 10 to 15% of oxygen will be converted into ozone. So therefore, the ozonizer will contain ozone as well as oxygen. Hence, it is called as ozonized oxygen. This is the method of preparing ozone in the laboratory. Ozone has angular structure. Both O double bond O bonds are equal or of equal bond length due to the resonance. So they have two oxygen to oxygen double bonds. So therefore, they have of same bond length because of resonance. The physical properties of ozone. Physical properties of ozone. Chemical property we will learn. Now, physical properties. First one, ozone is a pale blue gas. It is a pale blue gas having pungent odor. Pungent odor. It's a pale blue gas having a pungent odor. It is heavier than air. It is soluble in turpentine oil. It is diamagnetic. Remember this, ozone is diamagnetic. It does not contain unpaired electron. Therefore, it is diamagnetic. Chemical properties of ozone. What are the chemical properties of ozone? We will learn few chemical properties of ozone. And then we'll go for sulfur also today. Let's see. Time permits, we will do it. Now, chemical properties. The first property is decomposition. Ozone decomposes at room temperature, or it rapidly decomposes in the presence of catalyst at 473 Kelvin. So ozone decomposes at room temperature slowly. In the presence of catalyst, like manganese dioxide, at 473 Kelvin, higher temperature, it decomposes rapidly to give you oxygen. To give oxygen. To give oxygen. We can write O3 as O2 and plus O, or we can write this balanced equation. We can write 2O3 giving you O2. The next one is this ozone is a very good oxidizing agent. Why ozone is a very good oxidizing agent? Because, ozone is a very good oxidizing agent because this ozone will decompose to give oxygen, a nascent oxygen. Since it gives nascent oxygen, ozone is a very good oxidizing agent. Now, this ozone oxidizes lead sulfide. Lead sulfide is PBS, which is black. It oxidizes lead sulfide to sulfate. This lead sulfate, which is white in color. Lead sulfate is white in color. Sulfate is white in color. So addition of oxygen is called as oxidation. So ozone oxidizes black lead sulfide to lead sulfate. It is a white lead sulfate. It's a very important reaction. Similarly, reaction of ozone with metals. Reaction of ozone with metals. Metals like mercury and silver reacts with ozone . to give their respective oxides. Now, for an example, mercury on reaction with ozone, we get mercuric oxide, Hg2O plus O2. Likewise, if it's allowed to react with silver, silver reacts with ozone to give silver oxide, giving you oxygen. So reaction with metals. These are the chemical properties of ozone. And what are the uses of ozone? Before we learn the uses of ozone, we should understand the depletion of ozone layer. I'll erase this part and explain the depletion of ozone layer. Depletion of ozone layer. It is important, right? They can ask you, write a note on depletion of ozone layer. Why ozone layer gets depleted? Why ozone holes are formed? The main reason is oxides of nitrogen, mainly oxides of nitrogen, mainly nitric oxide, present as an effluent of supersonic jet plane. Supersonic jet plane reacts with ozone and causes depletion. So the main reason for ozone depletion is oxides of nitrogen, that is nitric oxide, present and the effluents and exhaust of supersonic jet planes are the main causes. So this nitric oxide, which is a gas, reacts with ozone to form nitrogen dioxide and giving you oxygen. So therefore, ozone keeps on depleting. Similarly, freons, fluorochlorocarbons, chlorofluorocarbons, CFCs, chlorofluorocarbons. These are also called as freons, used as a refrigerant, are also the reason for the depletion of ozone. So ozone depletion is mainly because of the oxides of nitrogen. Among that oxides of nitrogen, nitric oxide, which is an effluent of supersonic jet airplane, or it reacts with ozone and causes depletion. And chlorofluorocarbons, CFCs, freons, also, which is used as a refrigerant, is also a threat for depletion of ozone layer. What is the purpose of or importance of ozone layer? I'll erase this. What are the importance of ozone layer? Sorry, where is it? Importance of ozone layer, significance of ozone layer. What are the significance of ozone layer? See, ozone layer is formed in the stratosphere above 25 to 40 kilometers, the Earth's surface. Above, ozone is present above 25 to 40 kilometers above the Earth, right? Above the Earth's surface, called as stratosphere. Stratosphere. It absorbs UV radiation. It absorbs UV radiations. Like this ozone, oxygen will absorb UV light to form oxygen reacts with thought. Therefore,
Thank you, sir.
thank you for doing that. Okay, ma'am. Okay, ma'am. We'll meet next class, ma'am. We'll meet. Sorry. Thank you. Bye.
Thank you, sir.